Okay, in this exercise we computed K1, K2 by hands, and in this exercise we computed K1, K2, K3 by hands, and in this exercise also we had K1 and K2 and we computed them by hands. So let's learn how to compute them using MATLAB. Alright, so basically that's what we will do now. Instead of doing this hands calculation, three equations, three nonlinear equations with three unknown, or two nonlinear equations sometimes with two unknown, or etc., maybe more if you have more states. So instead of doing them by hands, let's learn how to do using MATLAB. Right? So you see this exercise, for example, instead of going over all this derivation to end up having K1 and K2, all this exercise, end up having, you see, all this derivation to get K1, K2 and K3, or this last exercise, same, instead of doing all this derivation. Okay, let's start with the first exercise, this one. Okay, go to MATLAB. In here, alright, so I want an M file. I go to this, okay, and maybe a new system. Okay, I have A 0 1 minus 1 minus 2 0 1 minus 1 minus 2. Okay, your matrix B is 0 1 0 1. That's it. Then your desired closed loop, like in here, your desired closed loop poles, desired closed loop poles are minus 2 minus 2 plus j times 2 square root of 2. Alright, and minus 2 plus and minus 2 minus. Okay, all what you need to do is k, use the term place, this function, it will do the calculation for you. Pole placement, do the name place. Pole placement, then do the name place again. Or you can use acre. Acre, we'll see it later briefly. It's an Ackermann method used also to compute the gain k. So AB and here use desired closed loop pole. Okay, let's use only one of them. Sometimes if one doesn't work, the second will work for sure. Sometimes acre works than this. Alright, so then this exercise 3, I will save it as exercise 3 into here actually. I call it exercise 3. Then I run, simply I run it. I should get K1 and K2. Alright, so let me go to MATLAB, network. So K1 equal 11 and K2 equal 2. You see, so I get K1 and K2. Also, let's do it using acre. For CMOS systems, they are unique. And 2. So 11 corresponds to the first pole. If you wish, what we studied here and this exercise, I have two poles, so I have K1 and K2. So in my case, K1 is the gain that will move the open loop pole, one of the open loop pole, to the plus location, to this location, -2 plus. So this is corresponds to K1, and this corresponds to K2. So K2 will move the pole from the open loop to -2 minus J, 2 square root of 2. Alright, so it's as simple as that, that's it. So let's do exercise after, just after, which is actually this exercise, right? Again, in this exercise, A is the following. Let's have your script and file. Alright, actually it turns out these are A, B, and A and B. Just don't waste time. So 0, 1, 0, 0, 0, 1, minus 1, minus 5, minus 6, and 0, 0, 1. That's for B. And your desired closed loop characteristic equation is -1, -10, and -10. Right? That's your desired closed loop characteristic equation. As simple as that. -1, -10, and -10. You can use acre or place, and this will call it exercise 5 as the name given here. Alright, so I run it and I see my answer here, 19, 115 and 15. So let's see the answer. $92, 115 and 15. So in this case 92 will move it to -5, -1, and 115 will move another pole to -10, and will move the third pole to -10 as well. So as simple as that. In one click, you don't need to do all the calculation. And the last exercise is here. You have this is A and this is B. Okay. Let's check A and B. Okay, A 0, 1, -10, 0. A is 0, 1, -10, 0. And B is 0, 1. And your desired closed loop pole are actually, maybe you can find them here in the last exercise. As we said, your desired closed loop pole are actually the pole of this. That's the desired closed loop characteristic equation. So you need to find, you have zeta n and omega, so you can find actually sigma and omega d, which is your real and imaginary part of your pole. Anyway, what you can do, you can have this polynomial and find the poles or the root of it. Well, just maybe I can have it here, saying a polynomial p equal one and 2 times zeta, which is squared 2 over 2 to zeta times omega n. Omega n is actually square root of 10. So here is zeta and here is omega n and omega n squared. This is your polynomial p, and root of p, maybe roots, you say roots. Okay, this is your roots of p, right? If you wish, I can just put it into the M file directly. So here I put P and then roots of P. Roots of P is your desired closed loop pole, as simple as that. So if you wish, you directly, or you do it this way. Desired closed loop pole equal roots of P. Simple as that. Then I don't need this one anymore. And this exercise, that's how to do. Okay, and this is, I'll call it exercise. Just I'm giving same name as the name you have in here. Exercise. Okay, just any name, and I run it. Then K0 and the other K 4.47, which is square 20, right? That's what it computed. See, the same. So then here is your calculation. We get K1 equals 0 and K2 square root of 20. Okay, fine. Then that's it about this exercise. Let's see in Simulink. Visualize it in Simulink. Let me take a simple block, which you know. Alright, I copy it. But this is, I don't need to do with you. You know how to take it and having it here. So here matrix. I'm using matrix multiplication, not element wise. So pay attention here. It's not really element wise. Alright, so here it's not element wise. What's the difference between element wise and matrix multiplication? Element wise, like element by element of the vector and the matrix. Here, matrix multiplication, like K times U. U is the input, as input. So then K times U, you get the output. You can have U times K. Okay, so you can see the help. You can have U times K. So then it will be like U first and K second. So then the dimension will be different, of course, you know. If you have K times U, is different than U times K. Alright? As term of dimension will be different. In general, if K is K1, K2, let's say K3, assuming. So then one line, 3 column. If that's the case, matrix K times U, U will be your X. X1 assuming X2, X3, because U as input U. So then it will be your X. So this is 3 times 1. So Ku is the following. K1 x1 plus K2 x2 plus K3 x3. Minus, so this is minus because this is here U equal minus Kx. Okay? And here is x. Anyway, I copy pasted. Let's put for each one, for each exercise, just to visualize it. Basically, for the exercise 1, we did here, for this exercise, I want to visualize, so A01, minus 1, minus 2. Let me run it directly instead of, okay, for exercise, this exercise, I run it. So when you run, your variables are defined. So you don't need now, okay, because I run, so now my A is defined. You don't need to do it this way, so then I say A, and because it's defined, I say B, and for C, I take the identity matrix. Here it's I2. Why I2? Because it's 2 by 2 dimension. Look to your matrix A. It's 2 by 2. Okay. As 2 by 2, and D. What's about D? And initial condition. So I will take initial condition of 1 1, which is your state. Your state at initial condition 1 and 1. Assuming, because I'm now showing you, trying to show you how we get there. Okay, so this is for one state. So you can have for another state, maybe for x1 and x2. So look at the dimension. A is 2, 2, and x is 1 line or 2 line, 1 column. Alright, here is 2 line, 1 column, then 2, 1, and here is 1 line, 2 column, or 2 line, 1 column. This is 2 line, 1 column, and this is 1, 1. Our U is a scale. Okay, here is a scale. Should be a scale. Function of 1. What about C? As it depends on the output. Depends on the output. If you want the output to be x, so then to have here that dimension of 2, so x means x1 and x2. If you want this to be output, so you take x as identity, and which identity is 1, 1, 2 dimension. And what about D in this case? If 2 dimension means you have here also, because y equal x, so then this is will be 1 line or 2 line, 1 column, 2, 1. This is 2 by 2 identity matrix. 2, 1, so 2 by 2, and x is 1 or 2 by 2, 1. 2, 2 times 2, 1, it's 2, 1. And this is, should be also 2, 1. Matrix D should be 2, 1 times 1, 1, which is U. So you get 2, 1. So then D is 2 line, 1 column. Okay, so then talking about matrix D is, of course it's 0 because y equal x, but you can put some dimension. It is 2 line, 1 column. So 0 is in the sense D then is like this. It's 2 line, 1 column. That's your D. So pay attention to the unit only, to the dimension almost. And the initial condition here, this is x1 initially equal 1 and x2 initially equal 1. I'm having some initial condition because you don't have input in the sense. Initially you have no input, just you have initial condition. Yes, So now you have your matrix A, B, C, and D. Your matrix A is again I said, and matrix B is, so is it so why didn't it change? And identity matrix is 2 said, and this is 2. Apply. Alright, your K is defined, it is in your workspace. Okay, so 11.2 for exercise 3, and that's it, that's all. So now I go and I save it as exercise 2, as exercise 3. I'll call it exercise 3 under sim link. Right. Let's run. And here we go for x1 and x2. So what you see on your, what we see here is actually the yellow one. The red is here, the yellow, which is one of the state, but here is the response of the second state. If you look at both state, they are as defined by as to get this desired response compared to the open loop. That's the open loop. Okay, here we can visualize even the open loop as well, or let me check, maybe I have a Simulink block for open loop. This is a open loop, let me take it. Okay, so even you can visualize them in one card. So then A and B, C, it looks like actually here it was for the one we want. Okay, so then I said A and B. Okay, apply. There we go. So basically what's visualized here in your PDF, solution, okay, it looks like the initial condition for R1 and 0 to get this result. The initial conditions are 1 and 0. Well, here they didn't show to us the initial condition. That's why I saw it's 1, 1, but actually it was 1 and 0. X1 starting at state 1, starting at initial condition 1, second and 0. Anyway, so now if you run it, this is your closed loop and this is your open loop. Let's put them together and see the yellow one here and there, and you see it is actually the same as what you have in your PDF. Okay, so you see here is the open loop, the green one, and here is the closed loop, which is the red one here. Good. So the other for the second state, which is initially started at 0. Okay, so here is for the second state. So you see it was very slow. I make it faster. Of course, in his PDF here, I mean his plotting, I open and closed loop together for one of the state. Good. So this is just to show you how you can plot them, having them in on Simulink. You can yourself do for the remaining exercises. Like what you can do now is in your homework.